Hi, my name is Micajah Schweikert, and this is my RCEU presentation. The numerical investigation of active flow blowing on a wing with conventional and non-conventional flaps. My mentor was Dr. Kanistras, and we worked with Mechanical and Aerospace Engineering Department at the University of Alabama in Huntsville. A little bit more about myself is I am a junior in aerospace engineering with a projected graduation in 2022. My role for this presentation and the included paper is the Computational Fluid Dynamics, or CFD, research. Any questions can be directed to the email on screen. My mentor, Dr. Kanistras, has a primary focus on flow control and runs his own lab called the AAFC lab, its link shown here. An introduction to the topic of active flow control. Essentially, we use energy to influence the flow over a surface. The picture on the left is a flow with no blowing. The picture on the right is the flow with blowing. You can compare the two, and you can see that the flow on the right, there is a deflection of the actual flow. This is caused by blowing or ejecting flow over the trailing edge of the surface. This relies on the Coulomb effect, which essentially states that flow curves over surfaces. The picture on the bottom right shows an airfoil with a circular trailing edge, with flow being ejected, this red high velocity area, into the external flow. This causes the flow to maintain its connection to the surface until about 60 degrees of that circle. The impact of Coulomb and active flow control is essentially we will have higher CL values for any given flow. This allows takeoff to be quicker, such as low runway environments like an aircraft carrier, or to decrease noise pollution by aircraft taking off. In other regime, we get higher lift and drag ratios, which essentially equates to efficiency. If we can get high lift values for a lower drag values, our engines don't need to push as hard to counteract drag, and this might open up the avenue for electric aircraft. The computational tools we used for this is ANSYS Fluent, which is a CFD program. CFD approximates Navier-Stokes solutions via a numerical method. A numerical method essentially uses meshes to discretize or break up a domain so that derivatives essentially become algebraic equations. CFD is not as reliable as an experiment because you are not physically interacting with the flow. You are simulating it, and some bad assumptions can lead to non-physical flows. However, CFD is very cheap and faster than experimental solutions because all that is required is the electricity cost of your computer. It also has easier visualization than experimental data because we already know the velocity at each point. Experimentalists have to sample this velocity. To refine the problem, we must also talk about other factors included. First is the Reynolds number, which can change with velocity. High Reynolds number, air behaves like air, and at low Reynolds numbers, air behaves like zero. Reynolds numbers dictate how much the viscosity means in the entire flow means. Flap curvature also dictates how long it will stick to the entire flap, because if it is more aggressive, it will separate quicker. So we test three different types of curvatures: a conventional flap, CF, which has no curvature, a DRF2 flap, which has high curvature, and a DRF10 flap, which has low curvature. And the point of this presentation essentially boils down to getting a good approximation of flow properties on different flap types using active blowing. The left picture shows the different DRF flaps. The right picture shows all of the variables considered in our analysis. Every permutation of every variable seen there has had data generated for it, but we can only include a small section of that data. The three coupled pictures we show in this slide are the conventional flap, the DRF2 flap, and the DRF10 flap, and we have velocity contours generated for each of them. In each pair, the left-hand side is the non-blowing case, and the right-hand side has blowing. You can see that the blowing largely reattaches the flow, which was originally separated in the non-blowing case. This increases lift and decreases drag. The future work is actually included in the investigation of the unsteady effects of active flow blowing using phase-lock PFD measurements. This is a document presented in the SciTech 2021 conference. And it boils down to the time effects of actively deflecting flaps. If you look at the GIF at the bottom, we have time deflecting flaps. So each frame you see here is a different time step. And then the flap deflects in time. This paper asks what happens if we add active blowing to this. And another thing we need to do is a validation and verification of the CFD results and calibration of the parameters used in the CFD results. As of yet, there have been no numerical verification done on the CFD. Any questions can be emailed to me directly at micajah.schweikert@uah.edu. Please include our RCEU poster presentation in the subject. If you're interested in our lab and what we do, there is the link for the lab. And other projects we have are morphing rings, where we physically change the shape of the ring, and plasma actuation, where we add plasma to change the flow over different types of rings. I would like to acknowledge Eli Merlock for the generation and production of wing models used and the testing apparatuses, and Tualsi for the experimental testing and analysis done in the paper. Thank you.